Alrighty, we are down to the assessment 3.3 review. Um, yeah, we're down to the assessment 3.3 review. The next video is going to be assessment 3.3, and yeah, then that's it for the unit. So let's go ahead and get started here. Get some exponential modeling done. Um, Nurse administers. Hopefully this is all fitting on the page. It's kind of hard to tell with the camera, but nurse administers 2 milliliters of medication to her patient. Medication will decrease 20% every hour. Write the exponential equation. All right. So um, F of t, we're starting out with 2 milliliters, so that's going to give us 2. But the medication will decrease by 20% every hour. So what this means is we're starting at 100%, but we're losing 20% every hour, so 0.2. So not only are we losing 0.2, but it's also in the context of an hour. So I'm going to take a look ahead. How much will be left after 3 hours? Okay. The time interval that we're writing the equation for is the time interval that we're going to be asked about later on. So we don't have to worry about any weird conversions later on. But we're starting with 100% and we're losing 20% every hour. So that means at the end of every hour, we are only left with 0.80% of what we had. And so that means that the equation this is going to be your equation. We start out with 2 milliliters, but at the end of every single hour, at the end of every single time, we only have 0.8 of what we started with every single time. All right, so make a prediction. How much medication would be left after 3 hours? Well, that is going to be f of 3 equals 2 times 0.8, and I'm going to put the 3 up there. Again, this is just one of those, you enter it into the calculator, read it from left to right. So that gives me 2 times 0.8 up arrow 3. Okay, 1.024. Oh, excuse me. That would be milliliters. So that is how many milliliters would be left in the patient after 3 hours. Okay. Well, that one's done. I just finished recording the videos for Quagsire and Bulbasaur, so I'm kind of glad to have a break with some of these questions. All right, so Rachel deposited 500 into an account, earning 3% interest annually. So we're starting out with 500, and we're earning 3% interest annually. So earning 3% means that it's a growth rate of 3%. So that means that we're starting with 100%, but the growth rate of 3% means that every year we're getting another 3%, which means at the end of every year we will have 1.03 times what we started out with. So we will have 103% of what we started with at 100%. And so if this is the number that represents what we're going to end up with after the rate has done its thing, this is the number we're going to put in to represent B, or the number in the parentheses, as I like to refer to it sometimes. So that's going to be the exponential equation for how much money she's going to get based on this interest rate. So how much money will be on the account after 25 years? If I had to guess, I'd probably say it. I doubt it would be over 1,000, but it would I doubt it'd be over 1,000, probably close to 700 or 800. But let's take a look. Let's give it a try. So f of 25, because again, because it's earning interest annually, the 3% is happening at the end of every year. So this equation is written in reference to years. And so if we're, so whatever time we have to feed in, it has to be in years. Thankfully, that's what we're given. So f is 25 equals 500 times 1.03 raised to the 25th power. Again, this is something that you can do on your calculator reading left to right, so I'm just going to do it off camera. 1.03 up arrow 25. Oh, well, all right, I stand corrected. Equals 1047. And because it's dollars, we got to include the dollar sign, so there we go. That is how much she would have after 25 years. So you know what, good for her. Let's see, in 2010, Apple stock was worth $12. In 2020, Apple was worth 70. write an exponential equation. Okay, well, presumably they want it to be referring to the Apple stock, so I suppose I can do that. So in 2010, Apple stock was worth $12. Again, going back to the very, very first worksheet that we did on this, if they give you years, they don't want you to actually feed in years into the X values. What they want you to do is use the years as markers, or because what happens is if they're asking, if you start in 2010 and they want to know what the answer is in 2020, they aren't interested in you feeding in 2010, 2020. What they're interested in is the change over time. So they're interested in how many years have passed in order to affect this change. So in that case, we're not looking at 2010, 2020. We're looking at 0 and 10. And so what that means is the first point we have is going to be 0, 12. And then the second point we're going to have is going to be, second point we're going to have is year 10, and that's going to be 70. So we've got 2 points, one of which is the y-intercept. It's the initial value, so that gives me equals 12 times b to the t. Now we just have to figure out what b is. The way that we figure it out is we take this point that we have here that we figured out from reading the text, and I'm going to put in 10 into the time, and then I'm going to put 70 into the stock value. So that means 70 equals 12 times b, whatever that is, to the 10th power. So I'm going to take both sides divided by 12. Yeah. So that leaves me with b to the 10th equals, and then 70 divided by 12, 5.83. Now we get to letting the calculator do all the heavy lifting. Let me move this down just a, move this over here just a little bit. Okay, yeah, I think you can see. Just in anticipation. So b to the 10th equals 5.83. So again, you can use fractional exponents if you want to. I haven't done it, and I wouldn't encourage you to do it either. But instead, what I will do is I will say b to the 10th equals 5.83. So that means I'm going to write down b to the 10th. So 10 is the first thing I'm writing down. Second up arrow, that gives me the little star house. That's really the best metaphor I can think of. It's the little star house. Now I'm going to write in 5.83, and that's going to give me 1.19. So that means that I've got a growth rate of, I've got a growth rate of 19%. But what really matters is I've got b. b equals 1.19. So now that I have b, I can write the exponential function f of t equals 12 times 1.19 to the t. All right, we're doing it. We're making it there. So make a prediction. If this trend continue, who writes this? Anyway, if this trend continues, what should Apple be worth today in 2024? All right, well, in 2000, so again, we're starting in, so today, they're saying 2024 or today, fine. So how much would it be worth today in 2024? Again, we're not interested in entering 2024 into the X variable. We're interested in, if you start in 2010, how much time has passed between 2010 and 2024. In this case, it's going to be 14 years. So if this is the equation that models change over every year, then we just have to find out what 14 is when we feed into it. So f of 14 equals 12 times 1.19 to the 14th power. And that's just going to be, again, looking at the equation, reading it left to right, times 1.19, up arrow 14, and that'll be 137. And there we go. That's the final / correct answer for it. Alrighty, we're doing pretty well here. Let's keep things going. I just looked at the back, makes me. All right. Let's take a look here. So we've got, I'm going to try to get this all in frame. Piece of machinery valued at $2,000 depreciates at 12% yearly. Oh, all right. So F of T, our initial value is 2,000. If it depreciates at a steady rate, what that means is it loses value, or rather, it decays at a steady rate of 12%. So if we start at 100% and we're losing 12% every year, what we're left with is, I think it's 0.88. So we're left with 88% of what we once had. And if we're left with 88% of what we had after the decay has done its thing on our original 100%, then that means that our B value is going to be 0.88. And that's how we write our equation. So make a prediction after 7 years, what would the machinery be valued at? Well, I want to make one thing sure, steady rate of 12% yearly. Okay, because it's every year, I don't have to worry about doing any weird conversions or changes. So I can just plug 7 into this equation here and solve for it. So F of 7 equals 2,000 times 0.88 raised to the 7th power. Okay, so I got 2,000. And again, I'm just reading it and entering it into the calculator as I read it going left to right, times 0.88 up arrow 7. Well, not too bad. That's going to be equal to 800, and I'm going to say, yeah, 817. So that's the answer for that one. All righty, boy, we're just plugging through this review. I guess by practicing with harder questions between Bulbasaur and Quagsire, we're doing pretty well with we're doing pretty well with the standard fare, what we're going to be asked on the assessment. All right, we've got 3 more, and then a little bit of a surprise at the end. So a scientist was conducting an experiment, started with 2 bacteria in a petri dish on April 1st. So F of T equals 2 times B to the T. All right. On April 15th, there are 32 bacteria in the dish. So how many bacteria will there be on April 30th? All right. They're giving us days in the calendar. So April 1st through April 15th. Again, as far as the passage of time is concerned, what we're looking at is days. So April 1st, April 15th, the difference between that is on April 1st, if time equals 0, which is what we're treating our initial value at. April 15th, there's 32. So the question is, what do we put for this value to represent days? Well, we don't want to do 15 and 1, because if we do 15 and 1, then we have to solve for using 2 different points. Well, actually, we can't use 15 and 1. If we did 15 and 1, that would imply that there was another value, but it would imply that there was an April 0, which there isn't. There isn't a day in April called 0. So we can treat April 1st as our initial value. Since we're treating April 1st as our initial value at time equals 0, if we want to find the difference between April 1st and April 15th, we just have to subtract 1 from April 15th, and that gives us a 14-day difference. And so since 14 days passes between there being 2 bacteria and there being 32 bacteria, I can write this point in as 14. So now that I've got those 2 points, so now that I've got this 1 point and this initial value, I can go ahead and solve for B. So that gives me 32 equals 2 times B, which is what I'm solving for, raised to the 14th power. This is not going to be a great growth rate. I can just call that right now. I'm going to divide both sides by 2. It gets rid of this one. So what that means is B to the 14th is going to equal 16. All right. So I'm going to go through and I'm going to do the whole star house trick. So let's start out with 14 because that's the number that is attached to my B variable as an exponent. Second, up arrow gives me the little star house icon, and then 16. So I'm going to hit enter. 1.22. All right, so B equals 1.22. Alrighty, we're in good shape there. That means that we can write our exponential equation so that f of t equals 2 times 1.22 to the t power. Alrighty, and everything is written in reference to days. So make a prediction. How much bacteria would there be on April 30th? So April 30th, I'm not going to write 30 because our first day was day 1. I'm going to write 29. So f of 29 equals 2 times 1.22 to the 29th. I'm going to just do that off camera because it's, again, literally just reading from left to right and then putting in what you read as you read it. Up arrow 29. Oh, that'll be 639. Well, 639 bacteria. Lovely. So yeah, that's that answer for us. I tell you, we're just plugging through on these. So next one, trying to get this centered again. So in 2016, there were 100 million Pinterest users. In 2019, there were 693 million users. Write the exponential equation. So just like with the last question, we want to establish what time zero is. What is our initial value? And if our initial value is going to be 100 million, which it is, if that equals 100 million, then technically time zero is going to be the year 2016. And so if the year that we start is in 2016, if we're looking at the value in 2019, which we are, there's 693 million users. But in 2019, the difference between 2019 and 2016 is going to be 3. So 3 years after our initial time, with our initial time is 2016, there were 693 million users. So that makes sense. So 2016 plus 3 is 2019. All right, everything's checking out. But what it means is that I'm going to take this point here with these values and I'm going to plug it into this equation in order to solve for b. So that gives me 693 equals 100 times this raised to the third power. Divide both sides by 100. And that gives me b to the third power equals 6.93. We're going to let the calculator do the heavy lifting for this. So I'm going to start out whatever power b is being raised to. I'm going to put that number first. Then get second up arrow, give me the little star house there. And then I'm going to put 6.93. And that gives me, I'm going to say 1.91. So b equals 1.91. All right. So all that means is now we can finish off our exponential equation. So 1.9 equals 1. Our exponential equation is this equals 100 times 1.91 to whatever the time interest is. All right, 1.91 times to the t power, and t is being measured in time. All right, we're doing pretty well. How many users could we expect in 2025? Oh, the long distance, the long time away of 2025, the future where we have jetpacks and colonies on the moon. So make a prediction. How many could we expect? Well, what I'm going to do is I'm going to put in the difference between 2025 and 2016, which should be 9. And so what that'll do is that will cover the time gap between 2016 and 2025, because every year they're growing they're growing by 91%. They're being left with 1.91 of what they started. So it's a growth rate, and so they're starting with 100%, growing, they're left with 1.91, growing, left with 1.91 of that, etc. And so what they're counting on is how many years have passed, because the amount of growth and the amount of users are completely dependent on how many years pass, not what number the years represent. So f of 9 equals 100 times 1.91 to the 9th power. Alrighty. So I'm going to say that's 33,830. And that's million. So that basically means that there are going to be 33 bill. There currently are 33 billion Pinterest users right now. So yeah, good for them. Alrighty, the last one. We've got some radiation, got some radioactive stuff to use. All right. It has an initial mass of 690 milligrams. Oh, well, all right, we're starting out pretty well. In 1997, and decays exponentially over time. All right, so we're not so lucky that it's going to give us the rate and we can solve it in one step. All right, all right. I was kind of hoping for that, but we're smart enough. We can keep this up. We can keep this up. So a measurement in the year 2001 found that the sample's mass had decayed to 390. So 390. And again, so we're starting out 1997 with 690 and 2001. So all we're doing is we're looking at the passage of time. So the difference in time for years between 1997 and 2001 is 4. So those are our two data points. So those are our data points. We know that the initial value is 690 in 1997, and then 4 years later it's 390. So let's just plug in the equation and see if we can figure out what the rate is. So that means 390 equals, yep, 690 times b to the 4th power. Divide both sides by 690. That means that b to the 4th is going to equal, I'm going to do this over here, 390 divided by 690. 0. I'll say 0.57. All right, so that means that we've got 0.57. I am going to bust out my little assistant here, and I've got b to the 4th power, means that I've got 4 here, and I'm going to use the little second little hat there with the star house, and I'm going to type in 0.57. That means that b is going to equal 0. I'll say 0.87. There we are. So now that we know that b equals 0.87, and we know that a equals 690, that means that ft equals 690 times 0.87 to whatever t value is. So, and again, the formula, the exponential formula that we wrote is in reference to years. So hopefully, yeah, here we go. How much mass could we expect in 2015? All right. So now we just have to figure out what the difference in time is between 2015 and 1997. I think it should be about 18 years. So again, we found the difference in time between 2001 and 1997 was 4 in order to get B. Now we just have to find the difference between 2015 and 1997, which like I said, I think it's 18. I'm pretty sure it is. So what that means is I'm going to feed in 18 equals 690 times 0.87 increase to the 18th power. Alrighty. I do this off camera again, so I've got 690 times 0.87 up arrow 18 equals, oh, I'll say 56.26. Alrighty, so after 18 years, there's about 56 milligrams yet left. All right, well, that's doing pretty well. That's not too bad. We are almost done with the review for the assessment. I think the assessment is actually going to have, oh, excuse me, assessment is actually going to have, as you can tell from my zooming in and out, the assessment is going to have a component that has to do with Desmos. So I'm going to switch over to Desmos, then head over to my computer, and we're going to take a look and make sure that I have everything framed up correctly first. There we go. Everything looks pretty good. All right. So again, I went ahead and I took a look. There are 2 Desmos problems at the end of the assessment review. I went ahead and I took a look at both of them, and I went ahead and entered in the data for both of them. We're basically just going to go from one table to the other, answer the questions, and then move on. Again, the Desmos questions, most of the time you're going to spend on them is going to be with the data entry. So, we'll just go ahead and go through with that. So the first one is year and U.S. national debt in billions. Boy, real fun one to start out with that. So with a label, we're going to go with year. And then for the debt, we're going to say dollar in billions. All right, so now I've got to fix what the range is. So for the x-axis, we're starting with 1930, so I'll say 1920. And then for the final one, I'm going to say 2040. So in this case, what I did was I'm just typing in the years. Could I go through and basically say that 1930 was year zero and then just calculate it out with 10-year variance? I could do that. The only thing that's going to change really is the regression formula. But the thing is, what you'll find is that the data itself that forms the exponential regression, it's not really going to change anything except maybe the initial value. And so as long as you keep the initial value in mind, it's not really going to change anything at all. So anyway, so I'm going to keep the years as they are. And with Desmos, it's probably just best to feed in the data on the table as you see it anyway. So for the y-axis, we're going to start at 16 billion. So I'm just going to put that at 0. And then for debt in billions, we're going to end with 27,000. So I'm going to put 28,000. All right, and there we go. Well, 27,700. So instead of 28,000, I'll just put 30. Like I said, more of an art than a science. So, yeah, we're starting out with 1930, and then our debt's going up exponentially like this. So we're going to use the model in order to get our linear regression. Well, not our linear regression, our exponential regression. Alrighty, so like I said, I put in the year, so the initial value is going to be really, really small. But what matters is the growth rate. So we've got 1.078% growth rate. So that means that it's growing at about 7.8% a year. For the let's see, for the coefficient of determination, our squared value, we've got 0.9988. So we can assume that this regression model is pretty good for the data points that we have. Let's go ahead and do a quick prediction because that's what the review asks us for. It's just these two, all right. Predict in what year the debt will be more than 75,000. So it's not just 75,000, it's 75,000 billions. So that is 75 trillion. So what I'm going to do, I'm going to hit the little plus next to the table, and I'm going to hit expression. And now the thing is before I would type in the year and I would find out what the debt was in the year, and it would just tell me. Now I've got to find out what year for the value is. So at 75,000, what that means is I'm going to do y. Whoops. There we go. I'll try one more time. I hit the button a little bit too many times. So for this one, I'm going to say y equals, and by saying y equals, that means that I'm going to be searching along the y-axis here, which with the label, I hope you can read it, is dollar in billions. So for this one, I've got y equals, and I'm going to type in 75,000, and that's going to be, all right, it's going to be all the way up here, all right. And it looks like it'll be in 2033, so not too far off. We don't have to wait that long for it. 1/10 of the year in, so a little bit into February, we'll be at 75. We'll be at 75 trillion in debt according to this model. So it looks like we got something to look forward to, and it looks like we got something to look forward to in about 7-8 years. So yeah, there we go. That's the first model. That's the first question there. Go ahead and close these ones down. For the second one, it's going to be years since purchased and the resale value of a Honda. So label year, but instead of 1883, we're tracking how many years since the sale. So the x-axis is going to be, I'm going to put it at -2. and then X itself is going to be, the top value is 10, I'm going to say 12. Let's see, the y-axis, it's going to start at 45,000, so I'll make the top value 50,000. And then for the label, I'm just going to put dollars. Then for the bottom value on the table looks like it's about 1071, so I'm going to set the bottom value to about 15,000. And that should help us out. All right, there we go. That's a pretty decent visualization for the data. Now, as we do before, as we do every time, I'm going to hit the little add regression. That gives us a linear regression, which, look, I got to be honest, I think the linear regression looks pretty good, and it fits it pretty well. So we'll just kind of keep this in mind that the R squared is 0.97 exponential regression. Yeah, see what I'm talking about? The linear regression is 0.97. The exponential regression is 0.93. So we'll take a look. What is the coefficient of determination? Like I said, it's a 0.93. What does that mean about the accuracy of the model? What it means is that the linear regression is more accurate than the exponential regression. So yeah, that's what it means. So we can move on from that. Predict the resale value of a Honda after 20 years, while assuming that it's still around after 20 years. Oh, who am I kidding? Cars like that never die. So again, we're f of x, and we're looking for years. So we're looking across the x-axis. So I'm going to say x equals, I'm going to set it equal to 20. And I know that, and I'm pretty close to where it is anyway, so I'll just say, so at 20, the value is going to be 9,173. I think that's reaching a bit, but I'm not writing the problem. And then predict how many years until the resale value will be less than 7,500. All right, so in that case, what we're doing, since x is years, we want to look at when it's equal to 7,500. So I'm going to type in y equals 7,500 here, so that's where it puts the line. And I'm going to scroll over and look for the year that it happens. Looks like it's about halfway through 22 years, so maybe in maybe in late May, early June, that sort of thing, of 22 years of ownership, late May, early June, that sort of thing. But yeah, so that should do it for the assessment review. There is exactly one last thing that we're going to do with the assessment review, and then one last thing we're going to do that has to do with the stock project. So hopefully you've been keeping track of that. If not, I'm sure that I have been on Canvas. And yeah, we're going to keep going, and all that is left is the assessment, and then this unit is done. So I look forward to seeing you all during the assessment day.